In this video, we're going to talk about L'Hopital's rule. So L'Hopital rule states that whenever you have a limit as x approaches to some value of like f of x over g of x, and if you like plug in c into this expression and you get like 0 over 0 or like infinity over infinity, we can evaluate this limit by taking the derivative on the top and the bottom separately. So this is equal to f prime x over g prime x. So this is the basic idea behind L'Hopital's rule. Let's start off with a very basic example problem. Let's start off with a very easy problem. So limit as x approaches infinity of 7x over 14x. So how can we evaluate this limit? So to evaluate this limit, first let's try to direct substitute, okay? So if I direct substitute this here, so I get 7 times infinity and then over 14 times infinity, then I just get infinity over infinity, which is indeterminate. So I can use L'Hopital rule for this. So I'm going to take the derivative of the top and the bottom separately. And these are polynomial function, so we can use the power rule. So x raised to the n power, the derivative is going to be n times x raised to the n power minus 1. So you just lose the exponent by 1 and then you multiply the exponent. That's the basic idea of the power rule, and you should know this. Now let's take the derivative of 7x. So 7x I can rewrite as just 7 times x raised to the power of 1, and now I'm going to follow this power rule here. So I'm just going to subtract by 1 and then multiply by 1 because that was the exponent. So 1 times 7 is just 7, and then I have 7x raised to the power of 0, and anything to the power of 0 is just 1, so we have 7 times 1, and then the derivative here is just 7. So this is the derivative of the numerator. And now for the denominator, we have 14x raised to the power of 1. So I'm going to subtract by 1 and then multiply by 1, and then this doesn't do anything much here because I'm multiplying by 1. So I have 14x raised to the power of 0, which is just 14 times 1, and then this is just 14. So now I have limit as x approaches infinity of 7 over 14. So 7 over 14 is just 1/2. So therefore, as x approaches infinity of 7x over 14, the value approaches 1/2. Let's try another example for sake of practice. So limit as x approaches infinity of x squared plus 5x plus 6 all over x plus 2. So if we try to do direct substitution, I'm going to get infinity squared plus 5 times infinity plus just 6 all over just infinity plus 2. And if I just combine these, I just get infinity over infinity, which is indeterminate. So I could use L'Hopital rule for this. So I'm going to take the derivative of the top and the bottom. So I'm just going to write the power rule here. So it's just going to be x to the power of n minus 1. This is the power rule that you can use for polynomial function. So the derivative of this top function is going to be x squared plus 5x plus 6. It's going to be x squared minus 1, and then we bring down the exponent, so we multiply by 2, and then plus 5 times x to the raised to the power of 1 minus 1, and the derivative of any constant is just 0. So then this simplifies to 2x plus 5. So this is the derivative of the top function. And now for the derivative of the bottom function, x plus 2, which is just going to be x raised to the power of 1 minus 1 multiplied by 1. And the derivative of the 2 is just 0. And here we have x raised to the power of 0, which is equal to 1. So this is the derivative of the bottom function, just 1. So limit as x approaches infinity of 2x plus 5 over 1. So now I could do direct substitution. So I'm going to replace x with infinity. So I have 2 times infinity plus 5. And I'm not going to write the division by 1 because it's just the same. So this is just going to give me infinity. So here the limit as x approaches infinity, the value is infinity. And it makes sense, because this function is a quadratic function and this is a linear function. So the quadratic function is always going to grow faster than this linear function because the quadratic function has a whole new degree. Let's try something different. So limit as x approaches 4 of x squared minus 16 over x minus 4. So look, if I direct substitute, right? So if I replace x with 4, I just get 4 squared minus 16 over 4 minus 4. And this is equal to 0 over 0. And 0 over 0 is indeterminate. We don't know the value. So we can use L'Hopital rule for this because we have an indeterminate form. So I'm going to take the derivative of the top and the bottom. So the derivative of x squared minus 16 is just going to be 2x. That's it, 2x. Because the derivative of this constant is just 0. So I don't need to write it. And the derivative of x minus 4, we know that the derivative is 0, so we only need to worry about this. So the derivative of x is just 1. And now so limit as x approaches 4 of 2x over 1, because that's our new limit that we got. And yes, make sure you keep writing this limit expression because your teacher is going to take off marks if you don't. So just get used to it, okay? Write it. So now I can do direct substitution because I don't get indeterminate form anymore. So if I do 2 times 4, I just get 8. So as x approaches 4 for this function, the value is approaching 8. Try this for yourself. So limit as x approaches -3 of x squared minus 9 over x plus 3. Go ahead and pause the video. So if I do direct substitution, so if I just replace x with -3, I'll get 0 over 0. So -3 plus 3. So this simplifies to just 9 minus 9 over 0, and then that's just 0 over 0, which is indeterminate. So you can use L'Hopital rule for this. So the derivative of this function, derivative of x squared minus 9, is just going to be 2x. And the derivative of x plus 3 is going to be just 1. Now we have a new function from taking the derivative. So at limit as x approaches -3 of just 2x over 1. So now you can replace 2x with -3. So 2 times -3 is just -6. So as x approaches -3, the value is approaching -6. Now let's try this one. So limit as x approaches infinity of x to the power of, okay, that was a horrible looking one. So x to the power of 4 plus 5x squared over e to the x. So if I do direct substitution, I'm going to get infinity over infinity, which is indeterminate. So I'll use the L'Hopital rule. So the derivative of x to the power of 4 plus 5x squared, using the power rule, x to the power of n is equal to n times x to the power of n minus 1. This is the power rule. So we can use it for this function right here. So this is going to be 4 times x raised to the power of 4 minus 1 plus 2 times 5x raised to the power of 2 minus 1. And now we can simplify this. This is just 4x cubed plus 10x. This is the derivative of the function on the top. Now the derivative of e to the x is just e to the x. Now we have a new limit expression. So limit as x approaches infinity of 4x cubed plus 10x over e to the power of x. So if I use direct substitution, I still get infinity over infinity. So I have to use the L'Hopital rule again and then again and again until I have like one of them as a constant. So like I don't have an indeterminate form. So the derivative of 4x cubed plus 10x is going to be 3 times 4 times x raised to the power of 3 minus 1 plus 10 times x raised to the power of 1 minus 1. And here I have 12x to the power of 2 plus 10. And the derivative of e to the x is just e to the x. But we're not done here, because this is still going to be indeterminate. So we'll have to take the derivative again. So the derivative of 12x squared plus 10 is going to be 12 times 2x raised to the power of 2 minus 1 plus 0, because this is a constant, so the derivative is just 0. So here we can simplify this. We get 24x, and the derivative of e to the x is just e to the x. It just doesn't change. And we are not done here, because this will still give us indeterminate form, because like 24 times infinity will give us infinity, and then we'll have e to the power of infinity, which is just infinity, and that's indeterminate. So we will do it again. So now the derivative of 24x is going to be 24 raised to the 1 minus 1, which is the 24 times x to the power of 0 and x to the power 0 is just 1, so 24 times 1, which is just 24. The derivative of e to the x is just e to the x. Now this is our new limit expression. So limit as x approaches infinity of 24 over e to the power of x. And now if I replace x with infinity, I get 24 over infinity. And 24 divided by a very large number is going to give us 0. So therefore, as x approaches infinity of this function, the value is approaching 0. And it makes sense because the function on the top is a polynomial function and the function on the bottom is an exponential function. And an exponential function grows rapidly and it will always grow faster than a polynomial function. Try these examples. Limit as x approaches infinity of ln x over x, and limit as x approaches 0 of tan x over x. I forgot to put a 0 there, my bad. Go ahead and pause the video. So, to evaluate this limit, let's try a direct substitution. So, ln of infinity, ln of infinity over infinity. This is just infinity over infinity. So, since we have an indeterminate form, we can use L'Hopital's rule. The derivative of ln x is 1 over x. And the derivative of x is just x. I take that back. It's just 1. Now that we have a new expression, limit as x approaches infinity of 1 over x over 1, we can just simply rewrite that as 1 over x. So limit as x approaches infinity of 1 over x. So 1 over infinity, and 1 divided by a very large number is going to give us 0. So the limit for this is 0. And it makes sense because of graph. So the natural log of x looks like this. And the y equals x looks something like this. Notice that the function x grows quicker than ln x. So this is bottom heavy, and whenever like the denominator is like heavier than the numerator, the infinity limit will always be 0. Now let's try to evaluate this limit. If we direct substitute, we're going to get tan of 0 over 0, which is just equal to 0 over 0, like because tan of 0 is just 0. And 0 over 0 is indeterminate, so that means we can use L'Hopital rule for this. So I'll get rid of this just so I can have more space. So the derivative of tan x is equal to secant squared. And the derivative of x is just 1. So now we can rewrite this limit because we got a new expression. So limit as x approaches 0 of secant squared x, and I'm not going to write the 1 because anything divided by 1 is just itself. So now we can plug in 0 for secant squared. So if you direct substitute here, it's going to be secant squared of 0, and secant squared, I can rewrite that as just 1 over cosine of 0 squared, which is equal to, and cosine of 0 is just 1, so 1 over 1, and 1 squared is just 1, so it doesn't really matter, which is just 1. So the limit as x approaches 0 of tan x over x, the value approaches 1. By the way, we can also like plug in like a number very close to 0 to see if we're on the right track. So for example, I could like plug in 0.001 over 0.001. I'm just replacing x with this number that's close to 0. So on your calculator, you could plug in that 0.01 divided by 0.001, and I got like 1.0000003, which is close to 1, right? And now I'm going to like plug in the same number but with like a negative value. Okay, so the reason why I'm doing this is because you need to make sure that the limit from the right side is also equal to the limit from the left side. So if I plug in that number on the calculator, I also got the same number as this. And make sure your calculator is in radian mode. Let's try one last example. So limit as x approaches 0 of 1 over root 3 sine of 3x over sine of 9x. Go ahead and pause the video and feel free to try this if you can. So first I'm going to replace x with 0. I'm trying to direct substitute, so it's just going to be, I'm going to focus on this part, these two, okay? I'm not going to focus on the 1 over root 3 yet. So sine of 3 times 0 and sine of 9 times 0, this is just sine of 0 over sine of 0. And sine of 0 is just 0, so that means this is 0 over 0, and this is indeterminate, so we have to use the L'Hopital rule. So now, the derivative of 1 over root 3 sine 3x is equal to, and you need to know that this is a composite function. So like composite function, basically there's like a function inside of another function. Notice that there's like a 3x inside of sine x. So this is a composite function. And for the derivative of composite function, we can use the chain rule. So the chain rule states that when you have like a f of g of x, the derivative is going to be f prime g of x multiplied by g prime x. That was a horrible looking g. So g prime x. This is the derivative for a composite function. In this case, we have f is equal to sine, and 3x is like the gx, the g of x. And this thing is just like, you're just multiplying. It's a constant. So the derivative of sine x is just going to be cosine. And then we multiply by g prime x. So the derivative of 3x is just 3. And don't forget that we had a 1 over root 3 because we're multiplying by that. Now we can rationalize the denominator. We'll like simplify everything, okay? So it's going to be 3 times root 3 over 3. That's after rationalizing it. And times cosine 3x. So this 3 cancels out. So we have root 3 cosine x 3x. Yes, that's the derivative of the top function. Now let's take the derivative of this bottom function. So the derivative of sine 9x, we can use the chain rule for that. So here this is the f and this is the g, and so the derivative of sine x is cosine, and then just 9x, the inside stays the same, and then multiplied by the derivative of the inside function. So the derivative of 9x is just 9. So we have, simplifying it, we have 9 cosine 9x. That's the derivative of the bottom function. Now we have a new expression. So limit as x approaches 0 of 3 cosine 3x root 3, over 9 cosine 9x. And now we can direct substitute. So we just replace x with 0. So 3 root 3 times cosine of 3 times 0 over 9 times cosine of 9 times 0. And yes, the inside here will just be 0. So we have cosine of 0 on both the numerator and denominator. And cosine of 0 is just 1. So we have root 3 over 9 times 1 times 1. And then anything times 1 is just itself. So we have root 3 over 9. And I'm just going to take this here. So now on our calculator, so root 3 divided by 9, we get 0.19245. I'll write it better. So 19245. This is the approximate value, but this is the exact value for the limit. Now that you know how to do L'Hopital's rule, thanks for watching.